Good afternoon, everybody. I'm Ian Walmsley. I'm the Provost at Imperial College London, and it's my great pleasure to welcome you all to this year's Institute for Molecular Science and Engineering annual lecture. It's great to see so many of you joining us online today. Although this is an online lecture, there is some housekeeping. Don't worry, I won't be telling you what to do in the case of an emergency and how to exit the room. I'll leave that up to you. But to note that this lecture is being recorded and will be shared online after the event. Following the lecture, there will be an opportunity for questions, and guests can submit their questions via the Q&A facility on the right-hand side of the screen. If you don't wish your name to appear in the recording, please select Post as Anonymous. The Institute for Molecular Science and Engineering is one of Imperial's global institutes, and it draws on the strength of our 4 faculties to address some of the grand challenges that face the world today. The Institute's activity are particularly focused on tackling problems where molecular innovation plays a critically important role. And it's therefore an honor for me to introduce our speaker today, Saiful Islam, Professor of Materials Chemistry at the University of Bath. Professor Islam previously completed his chemistry degree and a PhD at University College London, and then undertook a postdoctoral research fellowship on oxide superconductors at Eastman Kodak in Rochester, New York, in the US, followed by a lectureship at the University of Surrey. His research interests include computer modeling of new materials for lithium and sodium batteries, solid oxide fuel cells, and perovskite solar cells. He's received several awards, including the Wolfson Research Merit Award from the Royal Society and the Sustainable Energy Award from the Royal Society of Chemistry. Of course, he has many publications and many talks at international conferences, as well as giving very prestigious lectures, including the Royal Institution Christmas Lectures in 2016, which were, of course, broadcast on the BBC and can still be found on the Royal Institution website. His talk today is entitled Making a Material Difference to Green Energy, parenthesis, batteries included, and this will highlight the use of advanced modeling methods in synergy with experimental work that give atomic scale insights into novel materials that can be used for lithium batteries and for perovskite solar cells. Clearly, green energy is a very important topic globally today, and this talk will give us some fascinating insight into how new materials are being developed and will be critical to facilitate the next generation of clean energy technologies. So a very warm welcome to you, Saiful. We look very much forward to the lecture you're about to give us. Welcome.
Right, hope everybody can see that. I'm going to start with a thank you and then a confession. The thank you is to Ian for the kind introduction, but also to Nick Harrison for the original kind invitation. The topic I've picked on is making material difference to green energy, batteries included. And my confession is that I'm a bit nervous about this lecture. Nervous for a few reasons. One, I can't see the audience, so I can't gauge the reaction. And the other reason I'm a bit nervous is that I wasn't sure the level to pitch it. I know there'll be university students, university professors, there'll be non-scientists, the general public, so I wasn't sure about the level to pitch it. So I asked Nick, what should I talk about? And he said, about 50 minutes. So for the next 40 minutes, I'm going to give you a flavour of the type of research we're doing. And since it's a flavour, I'll start off with the menu. So as a starter of that menu, I'm going to briefly put the talk into context. I'll talk about energy materials and energy. Then I'll move on to the main course. The main course will be lithium-ion batteries. And then I suppose a small addition to that main course is, can we go beyond lithium So I'll talk about a few areas that are going beyond the current lithium-ion batteries. And then lastly, for dessert, I'll talk about solar. What's new in solar? And between that little image on the mobile phone is Shakespeare. I will start a new controversy. Was Shakespeare a chemist? As we know, the energy challenge is a very hot topic, both literally and metaphorically. And we're trying to move away from fossil fuels. And one of the biggest challenges is, can we get to low carbon alternatives? And they could be wind, solar, etc. So let me move on to the topic since we're a bit behind, and I apologize for the technical glitches. So materials are key, and you could say that energy conversion and energy storage are more important now than any time in human history. So I work in two areas, lithium-ion batteries and solar power. And what's key is that the breakthroughs for these two areas, new materials are important, new concepts, and a greater understanding. So what are the materials I'm looking at? So the materials I'm looking at are crystalline. So we live in a crystalline world. The most well-known crystals are the ones in our home, which is just salt, the stuff that you sprinkle on your rice, on your chips, and in my case, before a tequila shot. So sodium chloride is a very regular crystal structure. So all crystalline solids have this crystalline motif. They have this regular structure extended in 3D. This is sodium chloride. I'm sure it's familiar to the chemists amongst you. The large grey atoms are chloride ions, and the small white spheres are the sodium ions. And this structure is well known. It's actually adopted by silver chloride, which is at the bottom, much used in photography or old style photography, and also a compound like magnesium oxide, which is a catalyst. But these materials, these crystalline materials, aren't just rigid, they aren't just solid. There are some ions within these crystals actually are mobile. They can conduct. So that green ion that's moving is moving through the whole crystal structure. And that's very important for batteries, and I'll come back to that later on. Another important property of crystals is that they're impure often. They've got these defects. In this case, these beautiful defects or impurities impart beautiful range of colors, emeralds, rubies, whatever. And another important impure crystal is crystal meth, made famous in Breaking Bad. I should say the stuff I make is crystal clear rather than the blue stuff. So these are impurities and these are defects within crystals. So I'll move on briefly to the controversy. Was Shakespeare a chemist? In Midsummer Night's Dream, when Demetrius wakes up to see Helena for the first time, he says these words. He says, "To what shall I compare thine eye?" What he's saying here is that compared to Helena's beautiful eyes, crystals contain ionic impurities. So crystal is muddy. It's basically implying that Shakespeare was a chemist. So computer modeling. So when I go to parties, that's when I get invited, that is. Somehow the invitations dry up when you mention you're a chemistry professor. But when I do and they ask me, Saiful, what do you do? I say, I model. Obviously, I'm not modeling down the catwalk, I'm doing computer modeling. So this is a poster from the Royal Society of Chemistry. Not all chemists wear white coats, and I'm one of those chemists. I use computer modeling techniques, although I have problems with Teams and loading up PowerPoint presentations. But anyway, what are the aims of modeling? Well, there are three main aims. First one is it can complement experiment. It can help to interpret experiment. The second aim is, can modeling get new atomic insights that experiment can't get at? And lastly, can it be predictive? Can it predict new properties or new structures? And that's the most challenging part of modeling. So one of the best examples of modeling is this iconic photo of Watson and Crick building up the molecule of life, DNA, using clamps and retort stands. And they, using crystal data from Wilkins and Rosalind Franklin, they derived that the structure of DNA is a double helix. Nowadays on a computer, you can do that very quickly, within seconds. But this is a good example of curiosity-driven research that leads to really a range of scientific breakthroughs in molecular biology. And so that fundamental research is critical to a whole area. The modeling I do is a range of different time and length scales. So this is a plot of time scale up on the y-axis and length scale along the x-axis. So from angstroms to meters, I apologize for the American spelling, and from femto right up to years. So you've got techniques that are ab initio, which are first principles. There's the functional theory, which is sort of quantum mechanical, molecular dynamics, Monte Carlo, finite element, and continuum. As a chemist, I fall in the bottom left-hand corner, looking at electronic and atomic structure. So really looking at the atomic scale. So let me move on to the main course. The main course is the lithium-ion battery. And we all know that the lithium-ion battery helped to power the portable revolution. The portable electronics are now ubiquitous. Everybody has a mobile phone, which I would call really a supercomputer for what it can do. So this is me in the 1980s when I went to see the bands I like, the Smiths, The Cure and New Order. And this is what the youth are doing now with their mobile devices. And really, it's because of the high energy density in those lithium-ion batteries. And this is illustrated clearly in this plot here. So this is a plot of how much energy you can store per volume up on the y-axis and how much energy you can store per mass along the x-axis. So going to the right is a lighter weight and going to the top is a smaller size. And you can see lead acid is right at the bottom left, going through to nickel cadmium, nickel metal hydride, and lithium ion at the top right-hand corner. So you can show clearly, this shows clearly why lithium-ion batteries have helped to power that portable revolution. They basically store 3 times more energy than lead acid and the nickel cadmium. So I suppose the drive now is, can we store more energy than ever before? And the reason is that we want to develop better batteries for electric cars. I think every car manufacturer is developing a hybrid electric vehicle. You can't turn on the TV now without an advert talking about electric or hybrid vehicles. So the Toyota Prius, the Tesla and the BMW I'm showing there. I'm not a car engineer. I'm not even a big fan of Top Gear, but I love this schematic of electric car because of this label at the top, battery recharge plug, not to scale. Can you imagine that large plug, kind of pulling that large plug along at the back? So some of you might say, well, what is in a lithium-ion battery? And I'd say, well, that is a very good question. It's essentially an electrochemical sandwich. And like any sandwich, you've got 2 bread slices. In this case, one bread slice is an oxide electrode, and the other bread slice is a graphite electrode. And they're both layered materials. And like any good sandwich, you need a good sandwich filling. So the meat or hummus, if you're vegetarian or vegan, is a lithium-ion conducting electrolyte. So how does it work, this electrochemical sandwich? Well, when you charge your phone, so when you plug your phone in tonight or your laptop, lithium atoms moving from the oxide electrode to the graphite electrode, and that leads to that green symbol. When you discharge your device, when you're using your device, the lithium ions are going the other way, releasing electrons to power your device. It's a really fantastic example of electrochemistry in action. But there is an issue, and I'll come on to that. The current oxide electrode is made of cobalt, and we want to move away from cobalt because it's both toxic, expensive, and there are ethical concerns about its mining. So last year, this discovery finally got its Nobel Prize. It was much overdue, and John Goodenough got the prize. He's the oldest Nobel laureate ever at 97. For those not sure, John Goodenough is the one on the left, and the person on the right is a US president who actually believed in science and the scientific method. The other Nobel Prize winners are Stan Whittingham at Binghamton in New York and Akira Yoshino in Meiko University in Japan. So the current cathode materials, I mentioned the challenge. The challenge is, can we store more energy? Can we lower the cost? And can we make safer batteries? The current materials are layered oxide, shown here. So you can see the layers of lithium, which are in green, and the transition metal ions are in purple and yellow. And I'll come back to those materials in a second. The other materials are spinels. This is the prototype lithium manganese oxide. And the other family are these polyanion, lithium iron phosphate and lithium iron silicate, which I'll come back to as well. And they're currently being used right now. The layered oxides are used in Tesla and the spinel oxide in the Nissan Leaf. So when we think of charging, all of you would love your phone or your laptop to charge much faster. And it's basically determined by chemistry, how fast the lithium ions move, how fast the lithium ions diffuse through the materials. And this is important for charging. But is that diffusion fast? Is it 1D? Is it 2D? Is it 3D through the material? And particularly for new materials, that's not fully characterized. So this is the current material. The spheres are the lithium ions, and you can see the kind of 2D sheets. And the cobalt oxide layers are shown as octahedra. So they form these sheets of copper oxide, and lithium ions are coming out. And as in life, the important stuff is happening between the sheets. Sorry about that. And obviously being online, I can't hear or see your reaction. Anyway, that is the lithium cobalt oxide. But there is a problem. Actually, no, I'll show you how they diffuse. I hope this works. I know we've been having technical issues, but let's see if this works. I can see it on my laptop. Hopefully you can see yours. So this is showing a computer simulation of how the lithium ions move between those sheets. So for those keen followers of solid state chemistry, we'll know the oxygens are in red, cobalt are in blue, and the lithium ions are in green. And you can see they diffuse between the sheets in 2D. But what about new materials? So this is probably the most studied cathode material in the last 15 years, lithium iron phosphate. The structure I'm rotating here, the structure is made up of these iron octahedra in yellow and the phosphate tetrahedra in blue, and the lithium ions are in grey. And you can see straight away, hopefully, even if you're not a structural chemist, you can see the structure is very, very different to the lithium cobalt oxide. So why was it much studied? Well, basically, it's got a high voltage, and it contains abundant and non-toxic iron, and is also much safer because it's got very strong phosphate bonding. So it's seen as a potential game changer. Unfortunately, hasn't quite realized its potential, but it's still a very fascinating material. So the question I wanted to ask when we first looked at it is, how do the lithium ions move? So this is a slice through the structure. The iron octahedra are shown in yellow again. The grey are the lithium ions and the blues are the phosphates. So how do the lithium ions move? We predicted, this is from computer modeling, we predicted that it was a 1D conductor, a 1D channel, but not a linear path. It's a curved path. It's a bit like you and I, when we go walking or hill walking, we don't walk in a straight line. We go by the lowest energy pathway, and this is the lowest energy pathway. It's curved. This was a clear prediction. And what was nice is that a few years later, there was some elegant experimental work in Tokyo, which also showed that it was a 1D conductor, but what quite nicely from their elegant diffraction work, that it was a curved pathway. So from our modeling, we've showed both quantitative and qualitative agreement with experiment. And that's shown, if you do an overlap, that we actually predicted the curved pathway quite nicely. And we've done this for a range of different materials. I won't go through all the materials that we've looked at, but we've done this for a range of other cathode materials. So that was confirming the prediction. So what's new? This is slightly an extension of the main course. What's new in battery research? Well, it stems from this new funding body, the Faraday Institution, named after Michael Faraday. And within that Faraday Institution, there are a number of different projects. There's projects on recycling, projects on the solid state, and I'm leading a project on new cathode materials, which we've called CatMat. And the website is catmatproject.com if you wanted more detail. So we're leading this multi-center project, very large project, and it includes Oxford Materials, Cambridge Chemistry, Birmingham Chemistry, Liverpool Chemistry, and UCL Chemical Engineering. So it's really a large number of researchers, over 20 postdocs are on this project. And one of the areas that we're looking at is, can we replace the lithium cobalt layered oxide? And the next generation is what are called NMC materials, replacing the cobalt by nickel and manganese and reducing the amount of cobalt but increasing the amount of nickel. And then to increase the energy density, how much lithium you can store, how much energy you can store, there are lithium rich NMC. However, they pose problems in terms of voltage fade and voltage hysteresis. So we're trying to understand these materials much better to try and mitigate the problems in these lithium rich high energy density cathode materials. So that's one of the aspects of our work. Another project that's new is all solid state. The current battery in your phone right now has a liquid electrolyte between the electrodes. And this is a very rare event, but it does happen. A very rare event is that that liquid is flammable, so you can get some thermal runaway. So can you mitigate that? Well, one way of mitigating that is replacing the liquid by a solid, an all solid state battery. And that relies on a solid electrolyte. And the reason why that's much looked at, it increases the stability, the safety, and if you use lithium metal, it can increase the energy density. And there's a range of different materials being looked at. There's a family called garnet. There's a family called anti-perovskite, which I'll come to later on. And there's a family called the Lithium, the sulfides, which currently have the highest lithium ion conductivity. And if you want to find out a bit more, we published a review on these solid state electrolytes in Nature of Materials at the end of last year. And we got the cover image as well. The other new area is, can we go beyond lithium? And if you look at the periodic table, as a chemist, you could say rather than beyond lithium, you can go below lithium. And below lithium is sodium. Sodium has a similar chemistry to lithium. It just happens to have a higher mass and a larger size. And right next to sodium is magnesium, which actually has the same size as lithium, but double the charge. Beryllium isn't looked at, Be isn't looked at because it's highly toxic. So really, beyond lithium, there's a big research effort on sodium. So why sodium? Well, sodium is much more abundant than lithium, so you could actually make cheaper batteries than lithium, and you don't have to worry about its cost or its mining around the world. Because it's heavier than lithium, it probably won't be used in the near term in your mobile phone, but it could be used for what is called grid storage, storage for electricity. And that's when the wind isn't blowing and the sun isn't shining. We need energy storage, especially if we're going to have more renewables in our electricity grid, which is happening. I think it's around 25% of our electricity generation is from renewables, and that is bound to increase. So we need energy storage. So I finished the main course. Let me do a quick aside. This is a bit of an interlude, just to maybe, I can't see you, so you might be dropping off. You might be having, you might be going off checking your emails. But let me mention the Royal Institution Christmas lectures. It was Ian, when he introduced me, mentioned I did the Christmas lectures, and it was a real honour and privilege to be invited to do them. I grew up watching them at Christmas. I think many of our generation, we watched them. And I did the 80th anniversary one. So let me show you, I don't know if this will work. This is the that was the TV introduction to those lectures, which are actually online on the Royal Institution website, so you can see them. And I did the 80th anniversary of the first TV lectures. The first TV lectures were 1936. Actually, they were recorded at Alexandra Palace, not far from where I grew up in Crouch End in North London. Anyway, because of the 80th anniversary, I could invite Christmas lecturers past. And the first one to appear was Richard Dawkins. Despite my name, I'm a devout humanist and atheist, so it's a real honour to have Richard Dawkins on, and I reprised one of his demos. I did a pendulum experiment, except we replaced the metal sphere with a sphere with big spikes on it, and you have to watch it to see what happens, and that was in the first lecture. I then, in the third lecture, showed how a battery worked by using a lemon, and you can stick a copper nail in there and a magnesium strip, and you can generate about 1.4 volts. But I said to the Royal Institution, I want to go large. I wanted to go very large. So we built the largest lemon battery in the world. I got my group to buy 1008 lemons. We cut them in half to get 2016 lemon slices. So this was true cutting edge technology. You can groan at that point. And actually the toughest part, they told me, was putting the IKEA shelves together. Anyway, we generated a Guinness World Record. We generated 1,275 volts, and that is in the current Guinness manual, a Guinness World Record manual. So a Christmas prezi if you want that. Anyway, let's move on to dessert. Solar energy. The sun is obviously a light that never goes out. And what are the current solar cells? Well, it's dominated by silicon. Silicon dominates the solar panels, and the cost of silicon has really come down in the last 10 years. And that has really meant that the rollout of these solar panels has increased. But other generations of solar cells include cadmium telluride, something called SIGs, which is based on copper, indium, gallium sulfides, and also the dye cells. But what's new? What's been very topical in the last 5 or 6 years? Well, it's based on this word called perovskite. Perovskite is a naturally occurring mineral, and it's a structure type. And the naturally occurring mineral was discovered by a Russian geologist called Lev Perovskit, and it's named after him. And this is the structure. It's these TiO6 octahedra connected by their corner to form this beautiful 3D structure. And that large cation in the center is calcium. So that's the inorganic perovskite structure, the mineral. The new solar cell material is based on this inorganic perovskite. It's these lead iodide octahedra. The iodide ions are in purple, and instead of a calcium ion at the center, we have this organic cation, methyl ammonium. So this is methyl ammonium lead iodide. So it has the same perovskite structure, but it's now organic, inorganic. So how does a solar cell work? So again, like a battery, it's a sandwich. I've made the sandwich schematic a bit simpler. There's a glass layer, a contact, an absorber, which is the perovskite semiconductor, and a back contact. So how does it work? Well, when you shine sunlight, you've got photons. Those photons excite the electrons within that absorber, and you get those electrons are very mobile, and you get electricity. However, that process isn't highly efficient, hasn't quite mimicked nature. There is what is called electron-hole recombination. But anyway, what is the efficiency of these cells? So this is the efficiency up on the y-axis against the year of discovery along the x-axis. So in red is silicon. So the efficiency is light in, electricity out. Silicon has, this is just, I should say single crystalline silicon, has reached about 25%. The perovskite only 10 years ago was languishing at 3%, only 3% efficiency. And then within 10 years, it's gone up to about nearly touching 25%. So that's unprecedented. That rapid rise in efficiency has not been seen with any other material. And the original work, some of the original work was by Tom Miyasaka at Tokyo and Henry Snaith here in the UK in Oxford. So these perovskites have been revolutionary. They're a light absorber. They're easy to make. You can make them in the lab with solution synthesis. They're low-cost synthesis. They've got good electronic behavior, but one of the downsides is stability. They do have issues with stability. But one of the areas that I'm going to mention briefly is that in the near future, you're going to hear about tandem cells with silicon. So because of time, I might skip this bit. What I want to move on to what's happening right now. Well, as I said, perovskites do suffer from stability issues. And one of the ways is, can we marry the best of silicon with the best of perovskite in terms of their absorber properties and other properties? And that's what's happening commercially. So I think the first technological breakthroughs will be what are called tandem solar cells, combining perovskites with silicon. And you're going to hear more about that, I think, in the next 5 years. So concluding remarks. I know there was a glitch at the beginning, so I won't delay you much further. So my concluding remarks are some take-home text messages. The first one is, I hope I've shown you the intricacy and beauty of some energy materials on the atomic scale. I hope I've shown you how lithium ions move on charging in different types of battery material. I've shown you we can go beyond lithium, either solid state or sodium. And very briefly at the end, I've shown you what's very topical and what's new with solar. And the key word is perovskite. What's the future? What's the future? I think one thing is certain about the future. It's uncertain. We don't even know what's going to happen with the virus situation at the moment, but I'm an eternal optimist. I've always been an optimist. So I think these are challenging, exciting times, but I think science and engineering could produce some really exciting solutions to this really challenging area of clean energy and green energy. We're going to see more electric vehicles. We're going to see more solar power. Of course, there are going to be some materials issues to do with them in terms of access to resources, but I think we can actually deal with that through recycling and legislation. I'd like to acknowledge the researchers, collaborators listed there. I won't mention all their names. The funding bodies on the right, including EPSRC and Faraday Institution. And if you want some further information, if you Google Saiful Bath, you'll get my website. I promise you won't get a dodgy image if you Google Saiful Bath. And I'll end with a quote. And the quote comes from a really fascinating exhibition I went to right next to Imperial College, and that was at the Natural History Museum, or nearby to Imperial College. And it was an exhibition about Charles Darwin. And the quote, it wasn't from Darwin, from the great man. The quote was from a French philosopher, Marcel Proust. And to me, this quote really talks to me about science in general, but materials chemistry in particular. And the quote is, "The real voyage of discovery consists not only in seeking new landscapes, but in having new eyes." And on that note, I thank you for your attention. Thank you.
Brilliant, Saiful, thank you. I know you can't see the audience, but could I applaud for everybody? That was very enjoyable, thank you. We have a few questions for you, if you don't mind taking a moment to answer some.
Happy to take questions, and again, a big apologies on the glitch at the beginning.
Well, I'm sorry that happened, but you coped with it brilliantly, so thank you for doing that.
Okay.
I'll read out these questions because they've been typed in by the audience while you were speaking. So Anna Freitag has asked, could you say a little bit more about lithium sulfur batteries and what you think the prospects are for those?
Right. So lithium sulfur is, again, one of the projects within the Faraday Institution. For those not familiar with lithium sulfur, so here, the batteries I showed you were what are called intercalation batteries, where the lithium ions go in and out. There are other batteries going beyond intercalation, and lithium sulfur is one of those. Lithium involves a reaction between lithium and sulfur, but it does produce a high energy density. There's a lot of research effort. So to answer the question, I think there is a lot of potential. There's a lot of issues to deal with. I'm not active in this field myself, in the lithium, but I realize that there are issues to do with side reactions, polysulfides, so a lot of issues to deal with in terms of stability. So it's been looked at, and I think, as with any battery technology, it could have applications in the future. I think the problems need to be ironed out.
You think, a subsidiary to that is, do you think we'll end up with a whole range of different battery technologies for different purposes? Is that
yes, I mean, if you think about even batteries in our house at the moment, the battery probably in your alarm clock is probably not lithium ion, it's probably just a standard nickel cadmium. So there's a range of batteries already. Lithium ion batteries dominate rechargeable. I think for energy storage for the grid may not be lithium ion. It could be sodium, It could be something called redox flow, which I didn't talk about. It could be even, it might not be batteries at all. It could be, at the moment, it's pumped hydro dominates, so we just don't know.
Yeah, actually, James Nightingale has asked a pertinent question there, which is, how do you think sodium batteries will compare and compete with flow batteries in the grid balancing applications?
I suppose the simple answer is I'm not sure. It's hard. It's always hard to predict. I always think about our lives 15 years ago. Who would have thought that this mini supercomputer in our hand, this cell phone, which isn't really a phone anymore, could be ubiquitous. So it's hard to predict what will dominate in 15 years. But I think redox flow and sodium will definitely be in the mix.
Yeah. Okay. Another question we have from an anonymous listener is that according to the World Economic Forum, the demand on cobalt in batteries will increase by 2% and nickel by 25% between now and 2030. Yeah. Do you think that the NMCs are the right way forward? And where do we go in terms of battery sustainability beyond 2030? Can you have batteries without these metals? Is the question?
Yeah. No, that's a very good question. No, it's not just cobalt; it is nickel, and in the near term, these nickel type dominated cathodes will probably be used in the electric vehicles. But the questioner is correct. Nickel is a limited resource as well. So in terms of sustainability, can we move away from nickel and cobalt? And the answer is yes. The drive is to try and move away from those. The other aspect is that 98% of lead acid batteries are recycled, I understand. So I think there'll be greater legislation, particularly in Europe, to push for recycling. So you can't just dispose of your nickel and cobalt batteries. But yeah, I think natural resources and sustainability is going to be an issue that we have to address. Yeah.
Yeah, I mean, I'm thinking from a solid state chemistry point, that those batteries stopped working, presumably because of phase transformations within the battery, within the materials themselves and the recharge. So that's eminently recyclable, isn't it? You could.
Yes.
If you treated that as a rock, just calcine it, you could take the metals out, separate them, presumably.
Exactly.
Possible,
and I think it's a bit of legislation and a bit of really good science and engineering, because you want recycling to have economic benefits as well. So that kind of economic incentive, but to make that initial economic incentive, there's going to be some degree of legislation to make it worthwhile to recycle. Otherwise, it's so easy to dispose of things at the moment.
Yeah, much too easy. Yeah. Another question from anonymous. I'm not sure if it's the same anonymous. Is how long do you think it will take before we have solid state batteries in consumer products?
The how long it will take question is always a difficult one, because you could predict something like I remember when people were predicting hydrogen fuel cells in cars within a certain number of years, and it didn't quite materialize. So I'm loath to predict a time scale, but I'm always optimistic that there will be some advances. I mean, it might happen in 10 years' time, but there will be advances.
Okay, I won't ask you to read out the impact statement from the Faraday set, but I can imagine. We have a final question from Gerard Bree, sorry. What do you think of the prospects for lithium-ion batteries with water-based electrolytes?
Yes.
Okay.
I mean, I didn't cover all the areas that are being looked at, but that's a nice question, because one degree of sustainability is can we replace that organic solvent electrolyte with something a bit more benign but still a liquid? So there's there's research in that area, and aqueous batteries, ionic liquids. It's a beautiful area of chemistry research, because there's so many different elements of chemistry that can impinge in this area.
Yes, I worried a little bit about the thought of lithium and water, but yeah.
Yeah, I don't think they'll be in contact.
Good. A question from Tribeni Roy, who says, can you use reactive force fields for these simulations, or do you tend to use density functional theory?
I am not. I use a range. So some of the simulations are potentials based for those computational physics chemists out there. So there's a range of potentials based or force field based techniques I use, but then we go up to electronic structure ab initio MD techniques as well. So I'm not wedded to one particular type of technique. There's a range of techniques that we use. So yes, we can use reacts force field type techniques as well. Yes,
good. Well, with that, can I thank you, Saiful? That was a really interesting lecture.
All right. I have to take.
Forgive me. I hope everyone else found it interesting too. You're right. It's a strange situation not to be able to get some feedback from your audience, but I think if we were. Go on.
I'm just saying that it is really. I had this kind of fear that I was talking to, as if the computer crashed. I could be just talking to myself, and no one could actually scream at me and say, "We can't hear you anymore." Or so it's a really weird sensation talking to hundreds of people without knowing if they're actually there.
Yes, very strange. Well, thank you again. And I'd like to also warmly thank Professor Ian Wormsley, the Provost of Imperial College, for his continued support for the Global Institutes and for IMSI in particular, and for being kind enough to introduce the lecture today. So thank you, Ian.
Thank you, Ian. And I'm sorry I arrived late with glitches and didn't have a chance for a chat, but thank you very much for that kind introduction.
It was great to have you. Thank you, Saiful.
And I'd like to thank the IMSI team, who've put a huge amount of work and effort into making this event run smoothly, all the pieces that did run beautifully smoothly. So to Leah
yes.
Adamson in particular, and to Steph Pendlebury and Kieran Brothy. And then I'd also like to thank the central events team at Imperial College for helping us, Christine Taylor and Amy Brown. In addition to that, this is as our annual lecture, I think this is a good opportunity to say a huge thank you to Professor Claire Agyeman, who was with myself one of the founding directors of the Institute just over 3 years ago now. And Claire, having served her 3 years, stepped down this year. So I'd like to thank her very warmly for the huge effort she put into conceiving of, growing, and then managing the Institute over that 3-year period. And I'd also like to welcome Professor Amparo Galindo, our new IMSI co-director, who has recently come into post as the co-director of IMSI. And with that, simply to thank you all for attending. Thank you to all for listening and providing such stimulating questions. And with that, I would like to close this year's annual lecture for the Institute of Molecular Science and Engineering. Thank you all.